All right, let's dive into one of the most mind-bending technologies out there right now, generative AI. We're going to break down what it is, how it actually works under the hood, and really get into why this is such a massive leap, a leap from AI that just analyzes the world to an AI that can actually create things in it. Let's get into it. So for the longest time, the AI we all knew was what you see on the left, discriminative AI. You can think of it as the analyst. It's incredibly good at looking at existing stuff and putting it into buckets. Answering questions like, is this picture a cat or a dog? But now, look to the right. Generative AI is the creator. It doesn't just sort things. It learns the very idea of a cat, the essence of catness, and then it can paint a picture of a cat that has never, ever existed before. This isn't just a small step up. It's a whole different ballgame. Okay, so why is this jump from analyst to creator such a big deal? Well, because it's unlocking things we couldn't do before, everywhere. It's a massive productivity boost, right? It can write the first draft of code, or an email, or a whole report. It's like a superpowered assistant for creatives, helping artists and musicians brainstorm new ideas. And it's not just that. It's driving serious innovation, helping scientists find new patterns in complex data. This isn't just about doing things faster. It's about making brand new things possible. To really get how this magic works, we gotta look under the hood. We need to understand the language the AI speaks, its fundamental building blocks. There are really 3 core ideas we need to wrap our heads around. So, how does an AI even begin to read what we write?
Well, when you and I see a sentence, we see words. Simple enough. But a computer, it doesn't work that way. The very first thing it does is chop our sentences up into manageable little pieces called tokens. A token can be a full word, like happy, or just part of a word, like the ing in running, or sometimes even just a single letter. This whole process is called tokenization, and it's step 1 for turning our messy human language into something a machine can actually process.
So, now that the AI has these tokens, it needs to figure out what they mean. And it does this with something called embeddings. Now, don't let the name scare you. An embedding is just a long list of numbers, a vector, that acts like a coordinate. It places the token on a giant map of meaning, what we call an embedding space. On this map, words with similar meanings, like king and queen, are neighbors. But words like king and spaghetti are miles apart. This is how the AI starts to understand concepts and relationships, not just characters on a screen. And that brings us to the real secret sauce of modern AI, the attention mechanism. Okay, imagine you're translating a sentence from French to English. As you write each word in English, you're not just looking at the last word in French, right? You're looking back at the whole sentence, paying more attention to certain words that are more relevant. That's exactly what this mechanism lets the model do. It can dynamically decide which parts of the input are most important for figuring out what to say next. And that ability to dynamically focus, that's the key. It's what allows a model like ChatGPT to remember what you said 5 sentences ago and write something that's actually coherent and makes sense. It's not just one little component. It's pretty much the engine of modern AI. So we have the building blocks. Now, let's talk about the different kinds of architects who use them. See, there isn't just one type of generative model. It's more like a whole zoo of them, and each one has a totally different recipe, a different philosophy for how to create something new. Let's look at how a few of the big ones compare. This table gives us a great bird's-eye view. First up, autoregressive models, like the ones that power most chatbots. They're amazing for text because they basically write one word at a time, just like a person would. Then you have GANs, which are like a constant battle between 2 AIs, making them incredible at creating super sharp, realistic images. And finally, diffusion models, which are the kings of image quality right now. They work by basically sculpting an image out of TV static. As you can see, they each have their sweet spots, and they each have their own big weakness, too. I love these analogies because they really help you feel the difference. On the left, you have autoregressive models. They're like these methodical storytellers, right? They write a story 1 word at a time. Each new word is chosen based on all the words that came before it. It's logical, it's sequential. But on the right, diffusion models, they're more like sculptors. They start with a totally random block of noise, and then, step by step, they carefully chisel away at that noise until a beautiful, coherent image is revealed. 2 completely different ways of thinking, both leading to just incredible results. And you've gotta love the idea behind GANs. It's literally a game. You have one AI, the generator, who is the counterfeiter. Its only job is to create the most perfect fakes it can. Then you have a second AI, the discriminator, who is the police officer, trying its best to spot the fakes.
It's this epic cat and mouse game where over and over, the counterfeiter gets better and the cop gets smarter until the fakes are so perfect they're impossible to tell from the real thing. That competition is what makes GAN images so crisp. Okay, so we've got the concepts and we've got the models, but even the most brilliant recipe is totally useless if you don't have the ingredients. And to build the powerful AI we have today, you need three things, and you need them in absolutely massive amounts: data, computing power, and a community. Just to give you a sense of scale here, just look at this number, 5.85 billion. That is the number of pictures, each with a text description, in just one of the open source data sets that was used to train models like Stable Diffusion. The amount of data these things need to learn from it's just hard to even wrap your head around. And for a long time, the thinking in AI was just bigger models are better. Just build a bigger brain. But then researchers discovered something called the chinchilla scaling law, and it completely flipped that idea on its head. They found that to get the best performance, you can't just make the model bigger. You have to scale up the training data right along with it. It was this huge aha moment. The secret recipe isn't just about size, it's about the right balance between the model and its data diet. You know, none of this insane progress happens in a vacuum. It's almost all being driven by the incredible open source community. You've got libraries from companies like Hugging Face that let pretty much anyone play with these powerful tools. You have the public release of powerhouse models like Llama 3 and Stable Diffusion. And of course, these massive open data sets. It's a collaborative engine that's just pushing the entire field forward at a breakneck pace. And this brings us to our final and honestly, probably the most important part of the story. With all of this incredible creative power comes some pretty serious responsibility. Building amazing AI is only half the job. We also have to make sure these systems are safe, that they're ethical, and that they're actually aligned with what we humans want. And the challenges are real. These models can hallucinate. Basically, they just make stuff up, but say it with total confidence. Since they learn from the internet, they can pick up and even amplify the biases that are already out there in society. Of course, they can be misused to create fake news or malicious code, and there are still some really tricky questions around copyright and privacy. These aren't just little bugs, they're fundamental challenges we have to figure out. Now, the good news is that for every risk, researchers are working hard on ways to manage it. It all starts with cleaning up the training data, filtering out the bad stuff, and involves something called red teaming, where you have experts who actively try to break the model to find its weaknesses. People are developing watermarking to help us spot AI-generated content. And one of the most powerful tools we have is a process called RLHF, which is all about teaching the AI to behave itself. RLHF stands for Reinforcement Learning from Human Feedback, and it's kind of like a 3-step training bootcamp for the AI. First, you just show it lots of examples of what a good answer looks like. Then, in step 2, you have actual humans compare different AI answers and rank them from best to worst. You use that data to train a second AI, a reward model, that basically learns to predict what humans will like. And finally, you use that reward model as a judge to score the main AI, giving it a little treat every time it says something that the judge, and by extension us humans, would prefer. It's how we're teaching these models to be more helpful and harmless. So here we are. We've seen AI grow up from being a simple analyst to a powerful creator. We've peeked under the hood at its language of tokens and embeddings and the different ways it can create. But this final question, this is the one that really matters. The technology is here, and it's getting better at an incredible speed. The challenge for all of us now is to guide it, to make sure that the future it helps us create is one that's not just new and exciting, but one that is safe, beneficial, and, well, one we all actually want to live in. Thanks so much for tuning in.